Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Okay, as shown in front here, you can see we are going into a new topics of week number 5. So the topic is known as electrostatic field in a medium. So what we actually learned before, okay, so we talk about electrostatic, and we know that electrostatic is a special type of field where it contains only electric field, no magnetic field. So that should be one characteristics. And the second important characteristic of this field is that it is independent of time. Okay, and in our previous discussion regarding electrostatic, we know that the source to generate such field going to be stationary charge, and we denoted that to be volume charge density. And we have learned that the source going to generate many type of field, and to be more precise, we learn two type of field known as electric field intensity and electric field density. Okay, that should be the field, and from the field we'll be able to learn about important parameter in electrical world, which is potentials, and then we also be able to determine how much energy stored in a system of charge, and that system of charge contain what is the field known as electrostatic field. So all these issues we talk about, they are related to one type of medium. Okay, so the medium of interest that we discuss is only based on what we call it medium known as free space. Okay, so known as free space. So that should be all. Whenever we talk about all the parameters before, the medium that we assume it to be always must be free space. Therefore, we denote that with special parameter epsilon naught. But in real world, the medium not only free space, actually the medium can be defined, okay, the medium here can be defined based on our experience learning circuit theory or electrical technology, can be defined as conductor. What else that you can define a medium in electrical world? Or we can define it to be a semiconductor for those who want to work in the world of electronic, so you're going to deal a lot with semiconductor. Or we can also define the medium to be dielectric. Okay, so there are other medium that actually involved in real world. So what we learned before based on free space is not enough. Okay, so now we would like to migrate, or we like to change the paradigm from only base of medium free space into more general medium consists of, as you seen here, conductor, semiconductor, or dielectric. But to make the learning process a bit easy, we're not going to talk about semiconductor, because semiconductor will be taught in more detail in electronic subject. For us, we just want to introduce the change that happened to the electrostatic parameter when we consider other mediums, or not only free space. And to be more precise, we're only going to talk about two main mediums, which are conductor as well as dielectric. And we assume the semiconductor is going to be discussed in more detail by lecturers who are teaching you electronic subjects. Okay, so therefore that should be the concern that we're going to focus. And the way we're going to define medium, okay, how we categorize medium, okay, categorize. So how we going to categorize medium in electromagnetic subject? It's very simple. You need to have three main components. Yeah? First, you need to have the actual medium. So that should be the first thing that you need to have, the medium. Okay, number one. Okay, it can be conductor, it can be dielectric, so it doesn't matter. That should be the first component needed in our discussions. The second component needed should be what is known as applied field, number two. Okay, I'm going to put here applied field. Okay, so that's the number two. Okay, applied field in this case, since we are focusing on electrostatic field, the applied field in our case now going to be either electric field intensity or electric field density. So that should be the second parameter of discussion. When you talk about more general terms in real world, the applied field can be either magnetic field or electromagnetic field. But in current discussion, we're going to focus on only electrostatic field. That should be the second component. The third component of interest is going to be the charged particle. Okay, so this should be our third component. Charged particles. Okay, charged particles. Sorry about that, I didn't see it. Okay, that should be the third component. Again, I'm repeating. For us to categorize medium in electromagnetic world, you need to have three major components. The first one should be the medium, number one. So this should be number one data that needed in our discussion. Number two should be the applied field. The applied field can be either electric field, magnetic field, or electromagnetic field. But in current case, since we are in the world of electrostatic, so the applied field in this particular scenario is referred as electrostatic field. And the third important component for us to categorize medium in electromagnetic world is the charged particles. And for us, the charged particles is known as rho v, volume charge density. Okay, so for EMT, the way we define the medium to be whatever it is based on how charged particles respond to the applied field. Okay, that should be very important statement in order to categorize medium in the world of electromagnetic subject. So how the charged particle respond to the electric field? For example, if the charge move, we can assume the medium to be conductor. If the charge remains stationary, we can assume the medium to be dielectric. So that should be the detailed parameter that needed to be observed in order for us to categorize medium to be what in our investigation. So again, I'm repeating, the medium in EMT is categorized by looking into three major components. The first one should be the medium. The second parameter needed in the discussion should be what applied field that we give to the medium. And the third thing that we're going to observe, how the charged particle respond to the applied field. So that is how we identify medium in electromagnetic world. Okay, so you will see this idea going to be repeated when we talk about conductor later on, and we will talk about dielectric. Okay, so that's what should be the introduction of what we're going to learn. For those who want to read more, you can refer to our textbook. Okay, Sadiku. And then you can open to chapter 5 now. So it's a new chapter. So this is going to be the issue that we're going to discuss. So Sadiku discuss what we are talking about now in chapter 5. So a lot of example in that chapter that you can refer to, and you can go through example given in order to make you more understand about the issue under the category of medium in electrostatic domain. Because what we are doing now, we are transforming from the behavior in free space into more general situation known as other medium. So that's what should be the case. So how are we going to learn about this issue? So we want to make it systematic. So the learning process has been identified to be as such. So the first step, what we're going to talk about, current. Okay, that should be the first topic of discussion under the category of electrostatic field in a medium. Current. That should be the first thing we're going to discuss. Okay, what we're going to do when we talk about current, we're going to develop 3 model of currents. Okay, that should be the objective of that particular topic. 3 models of current, meaning that we're going to develop 3 equations representing our current. So remember, current is totally different than stationary charge. In the source of electrostatic field, we talk about the charge to be stationary. Okay, but now the charge in the real world can either be stationary or moving. So in order for us to make it more general regarding the charge, so we're going to introduce equation when we are saying the charge is moving. So that topic is known as current, because current can be also known as moving charge. Because what we talk about in the real electrostatic world, the charge remains stationary. But since we have medium now, for example, conductor, and in conductor the charge is moving, so it's appropriate for us at this stage to introduce the model of current. So we're going to talk about the charge symbol, which are stationary before. Now we're going to add parameter to indicate moving, and from that definition we're going to define it to be current. So I'm going to talk in more detail in that particular topic when we come to it later on. So after we finish talking about model current, the second main topic that we can discuss going to be conductor. Okay, that should be the second main topic of discussion under this particular segment of lecture, conductor. So when we talk about conductor, so the first topic discussed under the discussion of conductor going to be symbol known as conductivity. Okay, so that should be the first issue of discussion. Why we have to talk about this parameter? Because we know in real world there are many type of conductors, and how actually we define good conductor or bad conductor. So the way that engineer used to define good or bad conductor by a parameter known as conductivity. So that's why it's an important parameter to discuss when we are discussing conductor. So then after discuss parameter conductor, we're going to continue the discussion with this idea of conductor under static condition. Conductor under static condition. Okay, that should be the topic we're going to discuss, the second topic of interest under conductor. So after that, we're going to continue the discussion with what is known as conductor free space boundary conditions. So here we're going to discuss about what happened to the E field or electric field when it propagates from a conductor medium into free space medium. Because now we have learned about two important medium, free space has what been discussed before, and conductor, what we've been introduced now. So logically we're going to learn how actually the electric field propagate from one medium to another medium, since we at this stage learning two main medium. So therefore we're going to talk about how actually the field propagate from conductor to free space, and that issue known as conductor free space boundary conditions. So then the third major topic of discussion going to be the material known as dielectric. Okay, so dielectric going to be the third main topic. Here we're going to discuss about first dielectric under static condition. Okay, that should be the first topic under the category of dielectric. And the second topic going to be dielectric boundary conditions. Because as we know, similar to conductor, there are many types of conductors. In dielectric also the same phenomena happen. There are many types of dielectrics. So what we're going to discuss here, what happened to the electric field as it propagates from one dielectric to another dielectric. So what happened to the field? That's going to be discussed in more detail then. So in the final topic of the discussion under this issue of electrostatic in a medium, we're going to end the discussion with a simple application. Okay, so the application logically, a situation, a scenario which consists of medium conductor, free space, and dielectric. So when all these three different medium come into the problem, so we're going to do that example. So meaning application will consist of various medium, and we're going to make it simple by going into what is known as capacitance. Because as we know, capacitor consists of conductor, free space, as well as dielectric. So therefore that should be our main situation when we talk about application of our current topics. Okay, again we're going to discuss everything in more detail as stated here. Hopefully you can to follow my lecture based on this identify steps, and it's important for you to understand everything in systematic way, because for us to be able to solve problem in capacitance, we must be able to know what actually happened to the electric field that propagate in a conductor, as well as how the electric field propagate in a dielectric. So therefore you can see in EMT, again I'm repeating the statement, the subject that we learn here always interrelated. So that is the reason why electromagnetic subject is one of the toughest subject in electrical subject, due to that nature. Whatever you learn in week number 1 still relevant in week number 14. So they are interrelated. So I'm going to go to the next issue now, talking about the current now. So that should be our statement now, the current. So the logical step we're going to go to talk about current. So current is the issue now. Current. So for those who want to refer to the textbook, so this topic actually stated in section 5.3, page 182 of the textbook. So that should be the reference that you can refer to in order to understand more about what I'm talking about in this current lecture sessions. So current, as I stated earlier, current can be defined as moving charge. Okay, that is the simple way of defining current, moving charge. So let's talk about the charge now. Okay, so the charge that we visualized before is presented by what is known as rho V. Because volume charge is the more general way to represent charge in our discussion before. So let's talk about this issue. So let's assume that you have a structure as shown here. Okay, so you have a spherical structure as shown here. Okay, that should be our structure. So let's assume the axis of this structure is coinciding with a x-axis. Okay, and this structure actually a volume charge. Okay, so therefore we're going to assume now the structure is a volume charge. So meaning that this structure filled with rho V. So this is a volume charge structure. Okay, so let's take a sample here. So this is our sample now. I'm going to zoom in now. I'm going to draw the sample now. Zoom in. Yeah. So what I'm going to draw now, the sample to be as such. So what we have, you have just a cube structure now, very small structure. Okay, that should be my sample. Okay, so the sample actually is taken from this region of our volume charge structure. Okay, so all hopefully clear here. So to make it related to our actual axis here, so I'm going to define this side of my box going to be dx, small length of x, because we are referring to x-axis, so this is parallel to that particular region, particular axis, and this particular side of the box. Okay, so let's define that to be our ds, ds, area, small area. Okay, so what we can represent this sample box in terms of mathematics. Okay, the charge, okay, sample charge now, I'm going to say, so since it is sample, so for logically the mathematic for the charge should be what? Yes, dq, a small charge. Okay, if the whole structure having total charge q, logically the sample here must have magnitude dq. Okay, that should be the model mathematic to represent amount of charge contained by this sample box. And in terms of mathematics, we know that based on our volume charge model discussed week number 2, okay, going to be rho V multiplied with dV, correct? That should be the general mathematical representation of dq. And relate to the box here, what we can say, actually the rho V now multiply with d as dx. Do we agree on that mathematically? Yeah, because this particular side multiply with this length going to give us the volume of the box. So therefore we are represent the volume by these two terms, the small area multiplied with the small length. Okay, so that should be our model mathematics. So let's go to the next issue now. So if I ask myself what is in terms of physics we discuss current. Okay, current, if you look into the physics, okay, so I'm going to talk about current now. Current, okay, is defined as charge, okay, passing through the area per unit time. Okay, so that should be the definition of current. Current defined as charge passing through a area per unit time. So what I'm going to talk now, so how we want to make this particular sample move. Okay, because now when we talk about passing, we must make this sample move logically, correct? So how we introduce movement to this particular charge? Good. By introducing electric field. So by making that, by introduce electric field E such that, let's say in this case, in the x direction, we are causing this particular structure to move. Okay, I'm going to make it move. So I'm going to make it move to the direction of the E. Because we know in our force discussion before, okay, when there's electric field, there's a charge, we're going to introduce force. And the force will cause the charge to move. Is it correct? So therefore, by introducing E to this particular structure, we are causing the charge to move. Okay, what we can see from this simple movement, okay, initially the sample is on the left, blue color. When it moves, it's going to be shifted to the right. Okay, so I'm going to draw a black box now. Okay, that's what the effect of movement now. So assuming that the area of interest is the shaded blue area now, you can see what happened here. Due to the movement of charge, there are amount of charge passing through the shaded area. That's one parameter that you can measure. And as well as this, another parameter that you can measure is the time taken for the charge to move. Okay? I'm repeating again my statement. Due to the movement of the sample, the blue box, due to the introduction of electric field, now the blue box is becoming the black box. So as you can see, for the blue box to become the black box, it must pass through the shaded area, blue color there. So by observing that particular area, you can see at certain time, there going to be some amount of charge that passing through the area. Okay, so by that, I'm going to say to myself, I, okay, the definition of current is equal to the dq divided with the dt. Okay, because current defined as charge passing through. So charge is what? Charge is the dq. The dq, the charge is the dq. Yeah, passing through the area. So that should be the charge. And then another parameter that you can measure, how long it takes for the charge to pass through that reference area. So that should be our dt. So by dividing that the charge with the time, we are defining the basic definition of physics regarding current. Okay, now I'm going to relate the basic definition with our model now. So what we're going to see that the I actually equal to what now? Okay, dq is rho v d s dx. Agreed? Okay, that's taken from our model here. And then the dt, I'm going to just make it located at that particular position. Why? Because I'm going to introduce what is known as rho v ds ux. Because what we can see, okay, the sample drawn here is moving with the velocity u x. Due to what? Due to the existence of electric field introduced to the structure. So what we are doing, when we introduce electric field to the structure and the electric field in a vector term in x direction, you are causing the sample to move in the x direction as well, due to the nature of electric field and charge. You're going to introduce force. So with that, we introduce that behavior with this detailed mathematics. And then if I modify slightly the mathematics now, I'm going to introduce the J now. The J is known as current density. Okay. So what is J? Very simple. J actually current divided with area. So it should be rho V multiplied with U X. And for your information, current density is a vector. So Jx, because that's how we define current density. It's a vector entity. You must always obey the vector of the velocity. So therefore, since we are defining the velocity in the x direction, so the J now also must be in the x direction due to the introduction of electric field as what we shown here in the x direction. So therefore, that should be the way we defining the current density. And to make it more general, we are saying that the vector J now, so it's a vector now, should be equal to rho V U. Okay, so that should be the first model of current in our EMT subject. So we're going to denote this equation as equation number 1. And you can see it do agree with our definition of current earlier, where we define current to be moving charge. So as you can see from the equation that we developed, okay, current is known as charge that move. Okay, charge that moving. So therefore, that should be our current. And please remember, the current here is not ordinary current. It's known as current density. And to be more precise, we're going to call this to be convection current density. Convection current density. Okay, you have to see this current is different than the current that flow in a conductor. Okay, because in this particular equation, it does not mention the medium of interest. Regardless what medium, if you have a situation whereby charge move, that's going to be our current. Therefore, now you can see current can flow in a water, even though water is not conductor. So that current is known as convection current. Current can flow through the air, as you can see lightning. So therefore, that current also known as convection current. So this equation specifically mentioned for charge that move, regardless what medium that we are dealing. Okay, that should be the first model of current that we should know, convection current density. So earlier, we talked about current to be I, but now we represent the current to be J. So how actually we going to relate these two together? Okay, so what we're going to do now, we're going to relate I with J. Okay, so I'm going to write a statement here. I, which is our current model, okay, can be related to J. J is current density. Remember, I is current. Okay, J is current density. So using this equation, using I equal to the integration of J dot ds. So that should be current model number 2. Okay, so now we are relating the J and the I. So therefore, if the J is known as convection current density, so the I here is known as convection current. Somehow, if the J is known as conduction current density that we're going to learn later on, the I is known as conduction current. And in the end of the session or end of the semester, you're going to learn the third type of current in EMT. We call it as displacement current density. So if that is the case, so the I will known as displacement current. So the I will take the name of what type of J been introduced to that particular situation. If in this case, since the J is known as convection current density, so the I is known as convection current. Anyway, this is the equation that we can use to relate the I and with the J. What is I? I is known as current. It's a scalar. It's no direction, but J is known as current density and J is a vector. Okay, so therefore you can see they are totally different entity. In the world of power people, the people working in Tenaga Nasional Berhad, the way they're going to represent current, usually with the symbol I. For them, the direction is not important. The only important for them is the magnitude, because they always charge the customer based on the magnitude. The more magnitude of current you use, the higher price you have to pay. But for those working in electronic world, they work in a minute structure. For them, they have to know the direction, how the current move in that particular device. So for them, the way they represent the current, they must use J, since J is a vector, involve direction. So depending which area of field you're going to work later on as engineer, so you will use a current model accordingly. Okay, that should be the second model. So I'm going to go to the third model of current now. After that, I'm going to end my lecture, so I'm not going to make the video too long. Okay, so the third model of current is going to be this situation. So this is a very important model. So let's say that you have a cloud of charge. So this is our charge, cloud of charge. Cloud of charge. So this cloud of charge contain what we call the charge here Q enclosed. Qn closed. And we have learned just now a charge can move. Agreed? Let's say now we're going to assume the charge is migrating from inside this cloud to outside region. So this is the way we're going to represent the movement of charge. So because we just discussed about moving charge as current, so I'm going to introduce that now. So the charge is migrating now from inside the cloud to outside, and that particular black arrow, we can denote that as a symbol J. Okay, because we are showing that there are movement of charge. It's a vector now from inside the cloud to the outside region. Okay, what I'm going to do now, I'm going to calculate the total charge. Okay, I'm going to calculate the total charge. So I'm going to say, based on what I observe at the boundary here, so I'm going to say to myself, total charge, total current, I'm very sorry now, I'm confusing. Total current at the boundary now. So total current, we always use the symbol I, correct? How do I measure the total current at the boundary? Yes, using the model equation number 2, which is equal to J dot ds. Agreed? But since the word total here, we must make sure that it's completely closed. We have to calculate all the current that passing through this closed surface. That's going to give us the total current. So that should be the first method I can use to determine the total current from this diagram. The second approach that I can do to determine the total current by observing inside this volume. So the total current now. Okay, I. So what happened to the charge? Okay, because as you can see, as the charge are moving outward, we can see logically the amount of charge confined in this volume going to be decreased. Okay, and then we defined earlier, current is charge divided by time. So therefore I'm going to say it now, based on my observation inside the cloud, I can say the current also can be defined as the rate of decrease of charge. Okay, so again I'm repeating, I try to determine current, total current, based on two different angles. One based on how much current passing through the closed surface. Another angle of determining the current is by observing how much enclosed charge being reduced, because as we can see, when charge move out, whatever charge remain inside this volume going to be decreased. So therefore that should be my second approach to determine the current. Okay, and we know these two current actually the same. They must be the same. Okay, they must be the same. So now I'm going to say to myself, let's say I'm going to say that for the first equation of current J dot ds, it must also be equal to the rate of change of enclosed charge within the cloud, because they are the same. They are the same current. One calculated from the surface of the cloud, one determined from how much charge reduced within the volume. So they are the same now. Okay, so what I'm going to do now, I'm going to modify the equation here as what we know, that the charge here is a volume charge. I'm going to say d over dt integration of rho v dv. Remember, we are assuming the charge enclosed is a volume charge model. So therefore, rho v dv is the total charge. So I'm going to rearrange the mathematics now. I'm going to say to myself, J dot ds, the left hand side remain the same, and the right hand side I'm going to make it as such like this: negative d rho v over dt dv. Okay, so just rearrange the mathematics. So what happened now, as you can see, the left hand side of the equation referred to the surface integration, whereby the right hand side integration is related to volume integrations. Okay, so this is what we are observing. So now I'm going to make it based on the same platform of integration. What I mean by that, I want to convert the surface integration to be in volume term. So because I know on the right hand side the mathematics is in a volume term, so therefore logically what I'm going to do now, I'm going to convert the left hand side of this equation to be in a volume term. So how do I convert from surface integration to volume integration? Anyone know the method that we can do to convert surface to volume? We have talked about this in our previous lecture. Good, some of you already see it. We use what is known as Divergent Theorem. Remember that theorem we discussed? Okay, Divergent Theorem. So Divergent Theorem is a theorem to convert surface to volume or volume to surface. So now I'm converting from surface to volume. So what happened now? So surface becoming volume. So I have to use this term. divergence of J close bracket d dV. Okay, so that's how we convert from one integration model into another integration model. To be more specific here, from surface integration model to volume integration model. So once both sides in the same format of integration, meaning what here, the left hand side in a volume integration format, and the right hand side also in a volume integration format. So we can just take the inside part of the integration, ignoring the integration parameter, just the inside data. Yeah? So what I'm going to do now, I'm taking just the red box part of the term. So what we end now, we end with this mathematics. Yeah? Divergence of J now is equal to d rho v over dt. That should be the equation that we end now. Okay, so what we are doing, we just taking the inner part of the integration mathematics, meaning that we ignoring the integration model as well the dv part, so just consider the inner part. So this method we are converting what is known from integration format into point format. Yeah, this is how we do it. We convert from integration based mathematics into point-based mathematics. This is how we do it. We just ignore the front part and the end part of integration. We just take the inner part of that mathematics. So we are saying the inner part here must be equal to the inner part here. So that's how we convert. So that's what we end with. So this equation is our third model of current model equation that we want to use later on. And we need to know about this model, and this model we call it to be continuity current equation. Okay, I'm going to write it continuity current equation. Okay, so that should be the last current model we need to know before we migrating to the next topic later on, which is regarding conductor. Okay, so with that, we have developed successfully 3 current model. Okay, first we call it as convection current density. The second model is how we relate the I to the J, and then the third model of discussion, the third equation that we develop is known as continuity current equation. So all these 3 models are important. We will use them a lot in our future discussion. Okay, so I think I already take a lot of your time already. Thank you for your attention. Inshallah, we're going to see each other in our next topic. Assalamualaikum warahmatullahi wabarakatuh, and thank you.